emissions to know which is to use the dry low emissions. And I saw in the
Shabab, the first burner design, which is in the previous slide, the stagnation point reverse flow combustor, this consider the flow is coming at the inlet and leaving from the same inlet. So it's just the flow burn, the combustion. If you can get back to the previous slide, please. So here, Shabab, you see the fuel plus oxidizer are coming from the top of the burner, and the other part of the burner is just closed. So the exhaust gases after combustion will return back. So we have internal flow recirculation. The exhaust gases will be coming back and just passing around the flame. So this is a kind of exhaust gas recirculation that will result in lowering the combustion temperature. Lowering the combustion temperature, then in this case we can lower the NOx emission. Okay, so this is the first design. The second design is the dry low NOx emission. Dry low NOx, which we consider lean premixed combustion, as we said. Yeah. We premix air plus fuel under lean conditions, then we can lower the combustion temperature in this case by using excess air. We call it dry, Shabab, because there is also another version which we call it wet low NOx emission. Wet, in which we just inject water vapor inside the combustion chamber to lower down the temperature. We call it wet. But this wet analysis to treat the NOx emission, when we inject the water, this is called water. And usually in the gas turbine combustion, we have high temperature, and the metal, the whole of the combustor is at high temperature. So when we have cold water is coming to this in contact with this wall, just it cause a kind of erosion, and also it result in some also kind of corrosion even inside the combustion chamber. That's why wet analysis or wet treatment for high NOx emission, we just skip it. And the main common way actually is dry low NOx, or what we call dry low emission burn. Okay. Please go ahead, Mishari.
On the two picture down is compare between the conventional burner and the dry low emissions and the size of the flow injection in the dry low emissions is bigger to gain the high amount of air flow inside. Next slide. The environmentally burner, which is the AV burner, stand for the enhanced vortex burner. The ability of the technology is to achieve the NO emission in low PM gas turbines has targeted name environmental burner. AV burner geometry contains of two half coins shell, where is the signal offset in the radial direction with respect to the other, while the maintain parallel axis as shown in the figure.
So Shabab, I'm sorry Mishari for interfering, but this chapter is the most important one, and I think it will be some part of it will be repeated in the next presentation. But here Shabab, this burner design, which we call it environmental burner, usually in premixed combustion we premix air plus fuel. So upstream of the combustor we have flammable mixture, which is air plus fuel. So we have the flame inside the combustor. So the flame will try to propagate upstream, outside the combustor, because the flame can see we have fuel plus air is coming, and this is combustible mixture. So I will try to go and try to burn. So if we have the flame speed, flame propagating in the reverse of the inlet flow. So the incoming flow is coming in this direction. So the flame is propagating in the reverse direction, trying to go upstream. If the flame speed overcomes the flow speed, then in this case the flame will propagate upstream. It will go outside the combustor. We call this Shabab as flashback. The flame is flashback, and this may cause actually explosion. And we have already in our lab here, we have encountered this actually many times, that with the flame we have propagation of flame upstream in case of pre-mixed flame, because upstream we have a pre-mixed mixture of fuel plus air. Type to prevent kind of instability also as well. So to prevent this is one design, we call it environmental burner, in which the flow is coming in the tangential direction. The flow is not coming in the axial direction. It is coming tangentially, just coming, just circulating. We have a swirl. All of the flow actually is coming in the swirl direction. We have tangential component. So this just cause what we call يعني vortex breakdown just at the outlet of the at the inlet of the combustor. It creates a very strong vortex. So when the flame try to flash back, go upstream, this vortex actually will take the flame and get it back inside the combustor. So this burner blade prevents the flame to be flashed back, the flame to travel upstream of the combustor. This is the design, to just insert the flow in the tangential direction. We don't have axial component of the flow, just the flow is coming tangentially to generate just a vortex breakdown to prevent flashback. Is that clear يا شباب? The idea is clear?
يا دكتور.
طيب يعني I'm sorry for just cutting many times, but just I want to explain those ideas. Those are very important يعني. طيب let's go ahead مشاري. Sorry for just cutting the talk.
No problem. The fourth one is a micro-mixer combustion technology. There is the prevent plate burner. The prevent plate burner is widely used in the household and industry applications such as boiler. The overall effect was flame speed decreasing downstream experimentally in the prevent plate burner. The flame shape for three-hole categorization of D over A equals 2.3, which depend on the Reynolds number as shown in the figure.
So شباب also this burner is a kind of another burner for more flame stabilization. We said we have a problem with flame stability. Now we try different burner design. This burner design micro mixer is a perforated plate burner, just a plate and in which we have multiple inlet. So in this case, just we divide the flame. As you can see, the flame is just divided to many small flamelets, and this small flamelet are just stabilizing each other. And the inlet cross section for each flamelet is very small. So that means the velocity of the inlet flow will be very high. So when the flame try to propagate upstream, it will find the inlet velocity is very high. So it will push it down inside the combustor. So the idea here of the micro mixer burner is to have very small inlet section, divide the inlet section into multi-small inlet. That will result in multiple small flamelet with very small diameter at the inlet section. So the inlet flow velocity will be high. So when the flame speed try to overcome the inlet flow speed to cause flashback, it will not be able to do that. So just this burner design acts as a flame arrestor. It prevents the flame from being flashback. So this is the micro mixer burner. One of its main characteristic, it prevents the flame to flashback as well, like the case of environmental burn. Okay. So please go ahead, Mashari. So please limit this chapter 2. I know it will take a little bit longer time in the presentation, but in the next chapters, inshallah, we'll try to go a little bit faster because some parts here will be repeated again. So please go ahead, Mashari, and try to limit the time.
Okay, the main feature of this burner is the staging capability and scale capability and fuel flexibility. The fuel mixer play a major role in the combustion resulting the emission. As the global trend shift toward the micro technology development, this fuel mixture process is also research of mixing the fuel and oxidizer at the macro level. Thank you. Now with my colleague.
So, who is the?
So thanks, Mashari. Yeah.
Yazid, so brother, here I will just try to skip this part. Is this here يا شباب the idea of the high temperature membrane reactor? We have a membrane. This membrane separates oxygen in the feed side, air in the feed side, and it separates oxygen to the permeate side. And on the other side, we can just have methane. Then we can burn the fuel. So in this case, شباب, instead of just using, usually we have to separate the oxygen from the air. We have what's called the air separation unit. separately. Then we can get the separated air and then we can take it to run the turbine under oxy-combustion condition. Another way is just we can combine both of them together. We can have the separation process and the combustion process in one unit. This unit we call it high temperature membrane reactor, in which we have membrane. Above this membrane we'll have the air. It will separate. It is selective. The material is selective to the oxygen. So it have vacancies that can absorb the oxygen molecules. It have oxygen vacancies in its structure, in its lattice structure itself. So it can absorb oxygen and then it can take it to the other side. Then on the other side we can have the fuel, then we can have the combustion. Now we have the separation and the combustion in one unit. This membrane need يا شباب يعني energy or high temperature to be activated to separate the oxygen. So now the membrane, beside the membrane we have the combustion. So it can take part of the heat released due to combustion to be activated for oxygen separation. يعني this kind of design يا شباب, first of all it is compact, combine both processes together, oxygen separation and oxy combustion, and also it may save part of the energy used in the oxygen separation process, because here the membrane can be activated by part of the heat of the combustion and it reduces يعني the heat losses within the system. But this يا شباب, this is a photo that you can see right now. I have worked on this membrane on MIT when I was at MIT. And this membrane يا شباب, we used to get this membrane from Air Product in Boston. They provided us on daily basis, because actually each experiment I had to put this membrane and then I have to replace it back at the end of only one set of experiment, and I have to replace it because the membrane itself got contaminated and it is highly sensitive to carbon dioxide. So there are a lot of problems يعني regarding this new technology, but يعني we are not focusing يعني here in our course. Just we are talking here about the gas turbine. The combustion technologies in gas turbine under oxy combustion and the burner design and all of that. So I'm sorry Yazid for not letting you to go with this presentation, but just I try to summarize it. But yani this is yani beyond the scope that we are talking about. Yani. Okay, so it can be used in the replacement, as Yazid can show. It can be used in. I have already a number of patents on this, maybe 3-4 patents with our group as well, for the replacement of gas turbine combustion using ion transport membrane or ion transport membrane reactor. But يعني شباب, this is يعني a little bit beyond our talk. So let's focus on gas turbine. Okay. Sorry Yazid. So is this the last part of this chapter?
We have the last part is with Mustafa.
So which part, please, if you can just go?
This one.
International trends in CCS and the CCUS. يعني carbon capture يا شباب technologies, and the carbon capture technologies, we said we have oxy-combustion, we have pre-combustion capture, in which we capture carbon dioxide before the combustion process through, as we said, the reduction of heavy hydrocarbon to lower hydrocarbon. Then we can just separate carbon dioxide. We have syngas like CO plus H2. Then we can just have يعني partial oxidation of CO to convert it to CO2. And then we separate CO2, and at the end we are left with hydrogen. Then we can take this hydrogen as a fuel. And as I told you, hydrogen is the main trend. So this is in pre-oxy-fuel combustion. And we have post-combustion capture, in which we use membranes to separate carbon dioxide from exhaust gases. The other uses يا شباب, when we capture carbon dioxide, this captured carbon dioxide can be either used in, we can use it in as enhanced oil recovery. يعني Aramco have used this carbon dioxide just to inject the carbon dioxide. I think maybe in Al Kharis or Al Hassa or something, because there actually the oil is under very high level, يعني under low level, maybe 2 miles or something below the ground. So they can inject some carbon dioxide to just enhance the oil recovery, to have the oil to go up. This is one of the uses. Second use, we can do sequestration. Just we can capture this carbon dioxide and put it underground in the empty oil well. This is actually, we have different locations in the world in which we can just have injection of this carbon dioxide underground, and it reacts with rocks and it creates some crystalline structure. Yani at the end we can get rid of actually this carbon dioxide. The third option is that we can use this carbon dioxide يا شباب to convert it to some product. Here in Al-Jubail, we have the biggest factory in the world for the conversion of carbon dioxide to methanol through a hydrogenation reactor. So carbon dioxide, it reacts with hydrogen, then it can produce methanol. Now we can get benefit from carbon dioxide. Also, carbon dioxide can be converted to urea, which is used as a fertilizer in agriculture, and so on. But يعني شباب يعني I'm sorry for cutting Mustafa also as well, but يعني the time cannot help us. So please try to go through the book. It's a very interesting topic. But يعني I'm just trying here يعني to focus on gas turbine. As we said, we can have fuel flexibility. We have oxidizer flexibility. We can have different burner design so that we can get more stable flame under pre-mixed combustion. So thank you, Shabab, for this very interesting presentation. So I would appreciate yani going to the next group. So Mustafa.
Doctor, I'm just uploading the.
So
slide.
Mustafa was the last one in the first group.
Yes.
So yani, we just wanted to hear your voice. I'm sorry yani, for cutting you, but yani, we have to manage it. And we need to focus on gas turbine. So thanks, Mustafa, and thanks for the whole group yani, for the very interesting work.
Thank you.
Sorry, Yazid, as well. Yani, I just cut your talk, but yani, that's fine. The effort is very clear.
It's okay. Thanks. I got it actually. I understand very well. يعني الحمد لله.
Yeah. So inshallah, يعني, شباب, it's a good book يعني, to handle and to read about gas turbine, especially here in Saudi Arabia. Saudi Arabia, as I told you, is the world top country in using gas turbine. Okay. So please go ahead with group number 2, Ali.
Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Saeed Al-Marba'i. Today, me and my colleagues are going to present the gas turbine performance for different furnace technology. The next. Ali. Okay. So we'll talk about the okay. I was going to say about the table content, but it was skipped. No problem. So first, we know that most of our energy resources, such as oil, fossil fuel, and coal, are not clean energy due to the emission of the CO2 and the nitric acid, and so on. So as a result, we want to increase our energy without these emissions. So we have been inventing some technologies, which are 3 technologies, such as the oxy-fuel, and pre and post combustion. The next. So here we talk about the tri-low nitric acid and low emissions burner for gas turbines. We have talking about in chapter 3, which was about in combustion, that if the fuel has been reacted with the oxygen or injected with oxygen, the production will only be in CO2 and H2O. So this will lead to reduce the emission of nitric acid and the carbon dioxide, which will easily captured and separate from the water. Also, this will lead to reduce the size of the tank compared to the tank that comes with the air. Although this method is easy for us, it requires a huge power for producing oxygen. Also, the temperature that results from the combustion is very high. So we take some of our CO2 and circulate it to cool our system. So now my colleague will continue with the combustion operability of premixed oxymethane flames.
Okay. So this part of the presentation is simply presenting the experiment that was done to investigate the combustor operability of the premixed flames. So basically, the test conditions, I'm not gonna actually mention all of them. So the objective of this test is to examine the fuel combustion model as a gas turbine combustor. Okay, the head end actually, the head end.
So Ali, so شباب, excuse me, Ali. So يعني شباب here يعني we talk in the last chapter about the different technologies. يعني in this chapter we have just taken some of those technologies, including Oxy-Combustion and some other swirl burner in which you generate a swirl to stabilize the flame, and also micro mixer burner. All of this, and we implement it in our lab. So we have those experiments شباب that يعني Ali is going ahead to present here. Just those are some testing of those burner in our lab in a model combustor, but this model combustor can generate power within the same range of industrial gas turbine per unit volume per atmospheric pressure. Okay. Usually all of these tests, شباب, as I told you before, in gas turbine we design the burner in order to have minimum pressure drop, or almost the pressure drop across the combustor is fixed or constant. Delta B is equal to half rho V squared, and the density is for the mixture, which almost is the density of the air, because air actually is the dominating species, so which is constant. That means delta B is equal to half rho V squared. Delta B is constant, rho is constant. That means the inlet velocity to the gas turbine combustor should be constant in this case. With constant cross-sectional area, that means the volumetric flow rate to the gas turbine should be fixed. And that's why in all experiments we just fixed the inlet velocity at a fixed value, almost it is equal to 5.2. But why 5.2? Because actually we just limited the inlet cross-sectional area to 2 centimeter. Then يعني, as I told you شباب, I don't know if I said this or not, we are working here in the lab using bottles. We have bottle for oxygen, another bottle for methane, and another third bottle for carbon dioxide. And those actually are limited size of the gas volume. So after some time, maybe two set of experiment, we have to replace the cylinders again. So that's why شباب, we made the reactor size very small, but it is representative. It's a model combustor, a small combustor. The inlet area is small also. The inlet velocity is a little bit to just achieve a certain Reynolds number, so that we don't consume much gases. So يعني we try to reduce the rate of flow rate of gases in this case. That's why we made this combustor very, يعني it is not very small, but we made it يعني model combustor. That's why يعني this is the velocity. It's low velocity, but it can achieve the required Reynolds number for gas turbine operation. And we choose those values based on the inlet cross section of the gas turbine to يعني try to reduce the rate of consumption of the gases. So when we have one bottle of oxygen or something, it can run us for maybe 1-2 days or something, so that we don't run out of gases very soon. Yeah, we don't have even money شباب to pay for. So that's why. So please go ahead, Ali.
Okay. So I think you explained the very first part, Victor. So the experimental setup, as the doctor said, it is the pictures here. Okay.
So الشباب علي لو me, this is الشباب, the swirler here. The swirler just generate tangential motion for flame stabilization. And here we have O2, CO2, and we have methane. All of them are mixed upstream to create pre-mixed mixture. Then it can go through the swirler, generate a swirl. The swirl شباب just create a recirculation zone inside the combustor to stabilize the flame. And this is يعني the burner. The throat area here is 2 centimeter for the combustor heat end, and the inlet velocity is 5 centimeter. Please go ahead, Ali.
Yep. And I think I forgot to mention, Doctor, this is, you can see this end here is on the top, the conical one, is actually to prevent the swirl losses. So the combustor stability maps, there are 4 of them made in the book. They are basically the oxygen fraction against the equivalence ratio. They are trying to see the effect of those, and plotted against the contours of adiabatic flame temperature and Reynolds number, power density.
شباب here, if you look here يا شباب, our target of this study testing this burner is to generate this stability map. This stability map, as you can see, we have two lines. The lower line represents the blowout, which is when we work at part load condition or at lower equivalence ratio. We said the flame will blow out, the flame will just shut off. But if we work at higher equivalence ratio, close to stoichiometry, that means the flame speed will be increased and there is a probability to have flame flashback. So we have the upper limit يا شباب is the flashback, the lower limit is the blowout. And between those two lines, this is actually the safe range of operation of the gas turbine. So when we have a gas turbine in the industry working under oxy-combustion, then you can look here in terms of equivalence ratio, operating equivalence ratio, and in terms of oxygen fraction, you can say this gas turbine cannot work unless between those two lines, between the blowout and between the flashback line. And this stability map يا شباب can be applied to industrial gas turbine. You can see it is function of dimensionless parameter, which is equivalence ratio and oxygen fraction. And this combustor can generate power very similar to the same range of industrial gas turbine. So we can take this stability map and apply it to a gas turbine in the industry. And we can say if you run this gas turbine under oxy-combustion, you have to make sure that this gas turbine is working under operating condition between those two lines, between blowout and between flashback. Because if you work it at a point above the flashback, the flame actually we cannot sustain a flame. The gas turbine cannot sustain a flame, and under blowout also there is no flame. So we have to keep the flame operability between the blowout and the flashback in this case. So sorry Ali, but yani this is something very important to just indicate. Please go
ahead. So there are some, I don't think this is needed right now. The lecturer said already we can operate only between the two lines. Also, another thing that we got from the test is the flame microstructure. From the left picture here, the ones on the tops are fixed oxygen fracture, and the bottoms are a fixed equivalence ratio with different temperature. The one on the right, we're trying to see what's the effect of fixing the adiabatic flame temperature on the shape on the size of the flame. And why is that important? We can see that keeping the adiabatic flame temperature constant resulted in no change in the flame shape. Thus, if we know the flame shape, we can easily design the for the flame combustion. So for the tip of the flame, for the tip of the combustor, since we already know the length of the flame and its size. The model step is going to be discussed by my colleague Mohammed.
Okay, assalamu alaikum. My name is Mohammed, and now I will discuss with you the method LAS, or the large eddy simulation pre-mixed Oxy-flames.
Mohammed, I'm sorry for cutting up. Shabab, here when we run the gas turbine and we find the stability map, the line representing the blowout and the line representing the flashback, we find all of this line, the flame blowout and the flashback at fixed adiabatic flame temperature. So the flashback line is at fixed adiabatic flame temperature, whatever the value of oxygen fraction, whatever the value of equivalence ratio. And also the flame blowout also at a minimum adiabatic flame temperature for all points. The whole point in the line of the blowout are at the same adiabatic flame temperature. And so we have concluded, shabab, out of this experiment that the flame operability in a gas turbine is depending mainly on the adiabatic flame temperature. So we have learned how to calculate the adiabatic flame temperature in terms of equivalence ratio and in terms of oxygen concentration in the oxidizer. So you have to make sure also that the gas turbine is operated between the lower adiabatic flame temperature at blowout and the higher adiabatic flame temperature at flashback. Okay, so adiabatic flame temperature is the mean or a very important parameter in the design of the gas turbine combustor. so that we can keep the gas turbine operating between a minimum adiabatic flame temperature at blowout and a maximum adiabatic flame temperature at which we should have the flashback. Here يعني Muhammad, I will just cut this part because this is يعني numerical modeling, large AD simulation modeling. This is something يعني very advanced at this level. So in addition to the experiment, we can try the calculation as well using يعني softwares like OpenFOAM or ANSYS software, ANSYS Fluent. Try to get inside more deep inside the flame. يعني in the experiment يا شباب يعني here يعني we are trying to get our best to just try to capture the flame shape, try to get يعني measure the blowout and the flashback and draw the stability map, but we cannot get more in deep inside the flame. What is going on inside the flame, and also how the flow and the flame interact under turbulent reacting flow condition. So يعني the turbulence will get inside and also the combustion will take inside, and the case will be يعني very complicated. I don't like to go with large AD simulations. Those يعني model and this is something يا شباب is highly advanced. So inshallah if some of you will just continue in as a graduate student, so maybe in this case we can just handle this one. So just we can skip this part. Sorry Muhammad for this, but يعني this is beyond our focus here.
Okay, thanks.
So yeah, please go ahead for the next part.
I'm going to talk about oxymethane versus oxygen enhanced air flame for gas turbine application. Almost all of the days of combustion application use air oxidizer. The resultant exhaust consists primarily of carbon dioxide, water, and oxygen and nitrogen. Fossil fuel of the main source of the energy in most of country which produce carbon monoxide, and several agreement to minimize emission using carbon capture and separation are an irreversible solution. But the separation of CO2 from exhaust system air combustion is complex and costly. Oxy-fuel combustion, on the other hand, use pure oxygen as oxidizer, so the results produced are primarily carbon monoxide and water. The former can thus be captured at significantly lower cost after condensing the latter, and also the absence of nitrogen also offers two additional advantage, which almost no oxygen, no nitrogen oxidation, also exhaust volume, smaller exhaust volume, which allow us for use more efficient treatment equipment. Switching from air to oxy-combustion, however, entails different degree of freedom for combustion operability. Air is an assembled low-cost oxidizer, so lane application typically in air fuel gas turbine to control the combustion exit temperature. The separation of the air generate oxygen, on the other hand, pass to energy penalty, so the oxy-fuel application need to be operated near the stoichiometry to utilize both the fuel and oxygen efficiently. Also, flame fuel and pure oxygen have extreme temperature beyond the meteorological limit for most metals. Duration employed to control flame temperature by regulating part of the exhaust flame back into the combustor. The reactant are those fuel plus CO2 and carbon monoxide that as be dissolved oxidizer. Replacement of N2 with CO2 deduct also offer to flame characteristic, primarily because N2 and CO2 has different properties such as heat capacity, thermal conductivity, mass diffusivity, and dynamic viscosity. CO2 is known as to have advanced effect on the reactant rates, flame speed, and combustion efficiency. Consequently, oxy-fuel flame have narrow stability window compared to the air-fuel flame. The reducing stability of oxy-fuel flame to the larger heat capacity of the CO2 compared to nitrogen, which reduce the flame temperature and burning velocity. The retreated kinetic and lower burning velocity of CO2 flame allow them to resist flashback better than nitrogen. The minimum oxygen fraction of CO2 and CO2 carbon monoxide oxide needed to be replaced the stable of the air fuel flame, which 21%, was found in the latent to be in the range of 30% to 40%.
So it's okay, Abdullah. So is it yani this part here regarding the flame, the stability map? I think we'll talk about. That should be the last part in your presentation.
No.
So please, please, if you can just skip this part, we just talk about so that we can yani.
Okay.
Just
my friend, we can do that. Okay.
Okay. So brother, here yani also you can see the flame shape. Yani this is yani something in deep into research. Yani just we need to get the overall idea. Yani when we work shabab with carbon dioxide instead of nitrogen, so usually carbon dioxide have different properties. It have very high specific heat. So when we have combustion, it absorb actually due to this high specific heat, it absorbs a lot of heat by radiation, and it can result in lower combustion temperature in this case. And also it lowers the combustion efficiency. So the replacement of carbon dioxide, the replacement of nitrogen in air by carbon dioxide in oxy-combustion will result in lower combustion temperature and also inefficient combustion. That's why, shabab, when we work with oxy-combustion, we have to make the oxygen fraction in the mixture of O2 plus CO2 not less than 30%. Almost 30% can give the same performance like the case of air. Case of air, air have almost 21% by volume oxygen and 79% by volume nitrogen. So this 21 should be raised up to 30 in case of oxy-combustion in order to get the same performance. So please go to next slides. يعني here شباب, this is يعني what we can say. So please go next شباب. Is there many slides still? So I think يعني we can be done with. I will share with you here شباب again the stability map. You will find different paper at different Reynolds number that mean different inlet velocities, then we can get the stability map. But يعني this is يعني something you can look at. So I would prefer Shabab just to end up with this group number 2. I would appreciate Shabab sending me this presentation. You didn't send it right now up to now. And then we can move to group number 3, please. Okay. So group 3, I think you are left with almost 20 minutes. So thank you very much, Shabab, for group number 2 as well. This is a very interesting work and detailed presentation. So thank you for this input. So would you please move to group 3? So you have a Shabab a kind of 20 minutes. Please try to be concise. So please go ahead.
Can you see my screen?
Yes, clear.
Inshallah, we will present operability of fuel oxidizer flexible gas turbine combustors. Here's our outline for this presentation. We'll introduce this subject, then we'll talk about the oxidizer flexibility and the fuel flexibility in gas turbines. And then we'll talk about the stability of Oxy-flames. And at the end, we'll talk about the combustor operability of hydrogen-enriched premixed and stoichiometric hydrogen-enriched premixed and premixed oxy-propane flames. The introduction, the operability of gas turbines combusted by both fuel flexible and oxidizer flexible is highlighted and compared to the non-flexible gas turbine combustor. Several techniques have been introduced to reduce the greenhouse gas emissions that is harmful for the earth.
One candidate technique is oxy-fuel combustion. This technique has pros as it needs little hardware, so it can be implemented on existing power plants. Nevertheless, one downside is as the reaction uses pure oxygen, the temperature of the combustion is very high, which can raise some safety issues. Now Hassan will continue the presentation.
Assalamu alaikum. The Oxy-Combustion Flames, due to the availability of air, usually we use air in the combustion, but the unlike of pure oxygen, which relatively expensive. So when you use oxygen, we go with the stoichiometric amount of oxygen, and due to the lack of the nitrogen in the combustion, the temperature is extremely high. So to avoid this high temperature, one of the solutions is to dilute the oxygen with the recirculated CO2 emission to reduce the temperature. The oxidizer dilution, due to the higher flame temperature, the efficiency of the combustion is higher, and the melting capacity is higher also. The huge difference between the physical and chemical property of the nitrogen and the carbon dioxide observation were made, such as that this mixture has inferior burnout and darker flame, and as the oxygen fraction is reduced, the combustion efficiency drops. Now my colleague Abdulaziz Harani will complete.
Assalamu alaikum. First we'll talk about fuel flexibility in gas turbine. The focus on this section is made on hydrogen and enriched combustion as one of the main fuel flexibility approach for the control of flame stability in gas turbines. Due to hydrogen higher power density in burning, smaller fraction can reduce fuel consumption in gas turbine and internal combustion engine industry. Several studies reported that introduction of H2 gas with different hydrocarbon fuels increases the flame speed and extends the lean flammability limits. The effect of H2 enrichment on methane is reported that NOx emissions are reduced as H2 enrichment with the fuel mixture increased. And H2 enrichment reaction increase the concentration of flame radicals, which is O and H and O2, and thereby the rate of reaction will increase. Also, inclusion of H2 in the mixture of CO2 diluted oxymethane flames shifts both the static stability limits and blow out the flashback to Lerner side with increasing hydrogen fraction, as hydrogen improves the kinetic chemicals of oxymethane flames. Second, the stability of oxy flames. The combustion stabilization is one of the bottlenecks for the oxy-combustion technology in making its way to the replacement of air-based combustion technology. There are a number of effective factors for flame stability, including composition, manner of fuel, oxidizer, mixture, introduction in the combustor, turbulence level, and burner design. Combustion stability is divided into two categories: the static stability and the dynamic stability. The static stability of flames is defined by their blowout and flashbacks extinction limits, as these flames remain stable in between these two extremes. And the dynamic stability is the flame stability in terms of high sound pressure, which was generated in combustion system and coupled with acoustic fluctuations. And the information of this dynamic stability is also important, as it can cause wear to the parts of combustor, which moving with flow gases can damage the gas turbine components. and comparing the oxy fuel with air combustion and the replacement of nitrogen with CO2 results in lower flame speeds and combustion temperature in the oxy fuel combustion when compared to the air fuel. Due to this reason, the oxidizer mixture is not achievable, and therefore oxygen composition should be more than this minimum there should in the oxidizer mixture for achieving stable flames. Thank you.
Just a minute, I'll reshare my screen. Okay, can you see my screen?
Yes, it's clear.
So, compressor flexibility of hydrogen-enriched premix. As we said, oxy-combustion is a promising technology which can be easily retrofitted to an existing plant with a slight modification. In such a combustor, fuel is burnt with oxygen separated from air, resulting in combustion products consist of carbon dioxide and water vapor. Carbon dioxide is captured by condensing the water vapor out of the flow gas stream, and as we said earlier, combustion with pure oxygen is undesirable due to the excessive temperature raise in the flame zone. So part of the carbon dioxide from the exhaust is recirculated back to the combustion chamber to control the flame temperature. The operating conditions. This figure is similar to the figure in the previous presentation. However, the difference is that the inlet in here is hydrogen and methane, and on the downstream of mixing chamber is just below the inlet section combustor, a 55-degree swirler that is attached to provide the necessary vortex for the swirler stabilization of flame.
Khalid, please. So Shabab, here when we said we can use oxidizer flexibility, we can use hydrogen. Hydrogen in some cases, if we are not able to run the gas turbine right now with pure hydrogen, because still it requires some modification, we can use hydrogen enrichment. Yani the gas turbine is working using natural gas. Natural gas here, about 40% of the power produced in the kingdom is through natural gas, which is mainly methane. So we can use methane natural gas, but we can use a little bit, we can add more hydrogen, maybe 20% hydrogen of the total fuel, we can add hydrogen enrichment. But what is the function of hydrogen, Shabab? Hydrogen is highly reactive fuel. So we said premixed combustion flame are not stable under lower equivalence ratio or near part load conditions. The flame will blow out, it will just shut down. So we can enhance the reactivity under part load condition and also under lower equivalence ratio by adding some hydrogen. Hydrogen is highly reactive fuel, so that it can extend the stability limit of the flame. It can actually lower the limit for the blowout limit. And in this case, the gas turbine can be working under part load condition, not only at the rated load condition. We said premixed combustion, we cannot run the turbine away from the rated load condition because the flame blow out. Now, if we added some hydrogen, we can enhance the flame stability, and it will blow out actually at a lower equivalence ratio. And in this case, the gas turbine can work under a little bit part load condition or at lower equivalence ratio. So this is the idea of using hydrogen as a fuel enrichment. We can enrich the fuel with hydrogen to enhance the reactivity of the fuel. And then we can extend the flammability limit of the gas turbine. Okay, please go ahead, Khalid.
So the combustion of hydrogen enriched methane is carried out in a vertical premixed burner at the atmospheric pressure conditions, enclosed by quartz tube open to the atmosphere. The effect of velocity on flame stability. Increasing the velocity has two ways of affecting the flashback and the blackouts. The increased turbulence tend to increase the flame speed, and the increased flow rate decreases the flow time scale. And the azimuthal region found for the blowout limits suggests that the complex correlation of the flame velocity with the stability limits. In the figure on the right, for 3 different velocities, shows the limits of the flashback limits and the blowout limits. Flame shape analysis. With the pure methane, the flames can be seen to separate over the reactor to take the shape of the confinement. Increasing the hydrogen percentage is characterized by more violent and compact flames, implementing higher chemical kinetics and faster flame speeds. And increasing the hydrogen also will increase the noise of the combustion dynamics and increase until the flashback is observed. For the third velocity of 4.4 meter per second, the flashback occurs after 50% hydrogen fraction.
So Khalid, sorry Khalid for cutting. So يعني زي شباب يعني just to show you the flame shape, how the flame look like inside a gas turbine combustor, and are different operating velocity, different equivalence ratio, different oxygen fraction. يعني this is something deep into research. So يعني just we need to get the idea. You have to be able to يعني create overall idea about this. So I would prefer if you can skip those flame shape and يعني getting into details. So yes, hydrogen enriched. So please go ahead with the next part, Shabab.
Walid will continue the presentation.
Okay, thanks, Khalid.
Assalamu alaikum. Good morning, everyone. My name is Walid Al-Amri. I'm going to explain the combustor operability under stoichiometric of hydrogen-enriched conditions. So starting with the flame stability mapping. This figure represents the flashback and blowout limits with the variation of hydrogen and oxygen fractions at inlet bulk velocity of 6 meters per second and under stoichiometric equivalence ratio against the contours of constant adiabatic flames temperature. So it is observed that the hydrogen enrichment has an insignificant effect on adiabatic flame temperature, which is dominated by the oxygen fraction. So the stability limits show no obvious associated with hydrogen fraction, and the flashback reduces from 45% oxygen fraction with the pure methane combustion to 25% oxygen fraction at 90% of hydrogen fraction. So go to next slide. And the effect of higher flame speed due to the addition of hydrogen is partly neutralized by the high convective mass transport rate, resulting in only inappreciable variation in the blowout limit. Hence, the blowout limit shows a minor increase from 22% oxygen fraction for pure methane combustion to 16% oxygen fraction at 90% HF. So like the case of adiabatic flame temperature, the power density of the combustor exhibits no apparent relation with the stability map as shown in this figure.
So Walid there, Shabab, you can see Shabab the effect of hydrogen enrichment. As you increase the hydrogen percentages, that means we have high reactivity at Barth load condition or at lower equivalence ratio near the blowout. So you can see Shabab the lower line, see the equivalence ratio is the oxygen fraction. We said in case of oxy-combustion, we have to work at 30% oxygen fraction to get the same performance like air, and also to get a stable flame. Now you can see with hydrogen addition, you can see the oxygen fraction is even at hydrogen fraction 90%. you can see the oxygen fraction at blowout is about 15%. So this is actually due to the high reactivity of hydrogen. It can force the flame to work under part load condition, or also under low equivalence ratio and under lower oxygen fraction. But on the other hand, يا شباب, hydrogen addition, it will increase the reactivity. So if the flame is near the flashback at higher equivalence ratio, so in this case, the flame speed will be increased in this case. So there will be a tendency for the flame to flash back. So what we do, just we lower the blowout limit using hydrogen enrichment, and also the flashback limit will be lowered at equivalence ratio, at lower equivalence ratio. So yani, it is not preferred to have hydrogen enrichment above a certain level, because increasing the hydrogen concentration more will just lower the flammability limit for flashback. The flame will flash back at lower equivalence ratio. Okay, so please go ahead, Walid.
Next slide, please.
Walid, so please, we can skip this flame shape. I'm sorry for cutting, but okay. As I told you, this is something deep in research, but most importantly, we can talk about the flame stability. So please go next slide so that we can just...
Next topic is the effect of inlet velocity in flame stability. So
Sorry, Walid again. So this part also is the effect of velocity and Reynolds number. This is something related to the turbulence and how we can make perfect match between the flow field and the reacting field so that we can get more stable flame. This is much deep into research. So combustor operability under, okay, so please go with this part 2-3 minutes يا شباب. If you allow us, we can have 5 minutes. If you all agree, then we can just end up after 5 minutes. Please go ahead.
Assalamu alaikum. My name is Osama. We'll talk about the combustor operability of the pre-mixed oxypropane flames. This is the test condition. Go to the next slide. Next slide, please. There is the stability map of oxypropane flames. The plot is drawn for investigating the relation between the flame stability and the adiabatic flame temperature. The stable region between the two curves narrows down with the increasing of the oxygen fraction and emphasize the presence of the non-reactive dilute gas, which is CO2 in our case, for stable combustion. Also, the blowout curve show almost a constant adiabatic temperature, about 1,200 Kelvin. Next slide. This figure compare between the operability of oxymethane versus oxypropane flames. The dashed line curve represents the limit for the methane flame, while the solid lines represent the limit for the propane flames. It's observed that both flashback and the blowout limit of methane flame are reached at high equivalent ratio as compared to the propane flame for the same oxygen fraction. Since the adiabatic temperature of methane is higher than that of propane, this difference in the adiabatic temperature shifts the stability limit of methane to higher equivalent ratio as compared to the propane.
So Hassan, this is a very important point here. The adiabatic flame temperature play actually a main role in the design of the gas turbine and also in the operability of the gas turbine. Okay, and also when we change the fuel, that means we have changed the adiabatic flame temperature. So if you are working on a gas turbine and you want to change the fuel from methane to propane, you have to keep in mind that this will change the adiabatic flame temperature, and that should change the operability limit of this gas turbine. So I have to avoid working under higher equivalence ratio in this case if I'm using propane instead of methane. And you have to be able to understand that. This is the basic fundamental of gas turbine, that its design is mainly depending on the adiabatic flame temperature. When we change the equivalence ratio, change the oxygen fraction, changing the fuel type, all of this will change the adiabatic flame temperature. As we have learned how to calculate the adiabatic flame temperature. So if you have something يعني like this in practice in your work after graduation inshallah, so you have to keep you have learned how to calculate the adiabatic flame temperature, and when we change the fuel, you have to keep in mind that this will change the operability of the gas turbine. I have to make sure that the gas turbine is still operating under the safe limit between blowout and the flashback. Okay, so please go ahead, Walid.
In addition, the propane flame have wider flame stability region than the methane flames. We can conclude that the oxy-propane flames are more stable at lower oxygen fraction and higher equivalent ratio, where the oxy-methane flames are more stable at higher oxygen fraction and lower equivalent ratio. And that's it. Thank you for listening.
So Shabab, so thank you for all for the